We're going to look at the cascode configuration. Cascode comes from vacuum tube days. It means a cascade of two triodes, so together cascode. But in this video, we're going to look in particular at a cascade of two bipolar transistors. They still call it a cascode. Here's what it looks like. It's basically a common emitter amplifier and then a common base amplifier. So these two together have the same function as a single common emitter amplifier, but the high frequency characteristics or the high frequency performance is a little bit better. When you use a cascode, you can get around the Miller effect. Let's go ahead and get started. On the left, we have a common emitter amplifier, and the problematic parasitic capacitance is this one right here, the capacitance between the base and the collector. I'm drawing it on the circuit, even though we don't normally draw it. It's always there simply because the base of a transistor is fabricated right next to the collector. So because they're so close, you're going to have some parasitics. The reason why this capacitance is more of a problem is because you have an inversion. If you have a signal that goes up and down that finds its way to the base, that signal is going to be inverted when it makes it to the load resistor. And as we saw in my video on the Miller effect, an inversion is a big problem. Let's do a quick review of the Miller effect. The Miller effect says that if you have an amplifier with a negative gain and you have a capacitor connected between the input and output terminals, then we can model that capacitance as two different capacitors, one hanging on the input side and one hanging on the output side. If our original capacitance is C, then the Miller capacitance, or the one hanging here on the input side, is going to be C times 1 plus A. Here at the output side, the capacitor will show up as C times 1 plus 1 over A. It's only a problem for inverting amplifiers, and I'm assuming here that our gain is negative. If the gain is negative, then the capacitance is effectively increased in value, and that's a big problem because it looks like a low-pass filter. Let's draw out the input side of our common emitter amplifier here to see how that capacitance shows up as a low-pass filter. Now this capacitor right here forms a high-pass filter, and that's fairly easy to design around. You can just use a larger capacitor if you have a problem. But this capacitor that I've drawn in red is a parasitic capacitor. You can't just make it smaller. It's part of the device. It's part of the transistor. That's why it's a problem. We're going to go ahead and neglect the large capacitor here, though. Small signals can go right through it. The small signal is going to see resistor R1 in parallel with resistor R2. It's also going to see a resistance looking into that transistor. Rather than write it out, let me just call it R pi. And then finally, we have this red capacitor, which I'm going to model as a single capacitor connected to ground. So this would be our base collector capacitance, which we could find in a data sheet. And then we're going to have to multiply it times 1 minus the gain, or 1 plus the absolute value of the gain if the amplifier is inverting, and in this case it is. We can imagine that all the resistances sitting to the left of this capacitor can be rolled into a Thevenin equivalent resistance. The corner frequency of this low-pass filter is just 1 divided by 2 pi times that Thevenin resistance times our capacitance, which we can call the Miller capacitance. The problem is that a larger capacitor shows up in the denominator, and it's a low-pass filter. So as C gets larger, the frequency goes down, and it's a low-pass filter, not a high-pass filter. So it's going to reduce the maximum operating frequency of our circuit. That's just with a normal common emitter amplifier. Over here on the right, we have a cascode. This is going to largely solve the problem. We're actually still going to have the same base to collector capacitance here on the right as we did on the left. But the situation is going to be mitigated because I'm going to design this common emitter amplifier to have a lower absolute gain. A cascode is a common emitter configuration followed by a common base configuration. The signal starts over here on the left, winds its way through the first amplifier, enters the emitter, and then exits the collector. If we want the same gain with these two amplifiers, the key to making it work is to use the common base configuration as your gain stage, but use the common emitter stage just to give you the inversion. Because typically, people are using common emitter amplifiers because they need that inversion. So let's use a small gain for the common emitter stage and a large gain for the common base stage. Therefore, you get both. You get the large gain that you need from the common base, and you get the inversion from the common emitter stage. If the gain from the common emitter stage is a lot lower than what it was over here on the left, which I could call A1, then the Miller capacitance is going to be a lot smaller than it was with the circuit on the left. What about up here with our common base amplifier? Isn't the Miller effect a concern here? Well, not really, because this is just an AC ground. The capacitance is still here, effectively connected to ground, but it's not been amplified by the gain of the amplifier. It's a non-inverting amplifier anyway, so the Miller effect is not much of a concern. Let's find the gain of the Cascode amplifier by inspection. Then let's calculate it using a small signal equivalent circuit. That's going to take us a lot more time, but it will at least convince you that you got it right. First, by inspection. Let's label our load voltage. First of all, we're going to have an input voltage divider. We're going to use impedance reflection here, but the question is whether we want to use impedance reflection to bring the base resistors over to the emitter or to bring the emitter resistors over to the base. I'm going to bring the base resistors over to the emitter, so I'm not going to use them here for my input stage. R2 is connected to an AC ground, so my voltage divider here is just going to be R3 in parallel with R2, and then we have our source resistance in the denominator. I'm not using impedance reflection, so I'm neglecting the resistance looking into the base. We're going to include it in our gain stage, though, so it's all good. I'm going to label RE1. We'll call the top transistor number 1, and we'll call the bottom transistor number 2. We now need the gain of a common emitter amplifier. We know it's inverting, so let me just write a negative sign. And you might recall that it's the resistors attached to the collector divided by the resistors attached to the emitter. Attached to the collector, we have RE1 that goes to an AC ground through the base. Now for the resistors attached to the emitter, we have RE2, which is in series with RE1, which is in parallel with RE. And those are in series with all of the resistors on the base side that I need to reflect across the red line. Now let's clean that up a little bit. So that takes care of our common emitter stage. Now we have the common base stage. We don't have any voltage divider here between our common base and common emitter stage. There aren't any resistors hanging off this line, so the signal fully is transferred. The gain of a common base stage is simply the resistors attached to the collector divided by the resistors attached to the emitter. It's non-inverting, so attached to the collector we have RC in parallel with RL, and then down here we have only RE1 attached to the emitter. RE1 cancels, so basically we have an input voltage divider times what we have attached to the collector divided by what we have attached to the emitter. It's almost like a common emitter amplifier, a single common emitter amplifier. Let's convince ourselves that this expression is correct by deriving it from the small signal model. Let's draw an AC equivalent circuit. There's our source, and there's our source impedance. We now have a resistor R2 that leads to an AC ground. Then we have a resistor R3 that also leads to an AC ground. Now we have the base of transistor 2. Let's label the base current IB2. There's little resistor RE2, and I'm going to roll these two resistors into one. Transistor 2 acts like a current source at its collector, and it provides a current of beta times IB2. And now we find ourselves at the emitter of transistor 1. Let's draw the little emitter resistance RE1. The base is attached to an AC ground, but we still have base current IB1 flowing into the transistor. The transistor derives a collector current of IB1 times beta, and it pulls those through two resistors, RC and RL. We have up here our output voltage, VL. Let's now simplify our source a little bit by replacing it with a Thevenin equivalent source and a Thevenin equivalent resistance. The source will be providing the same base current as it was in the last drawing, IB2. I'm now going to combine these two resistors into one, and I'm going to just call it R sub lowercase e. We now have beta IB2 being pulled through the circuit by transistor 2. We now nearly have enough information to solve the circuit, so I'm going to start writing equations. First, let's look up here at our load. I want to apply Ohm's law across this resistor. V equals IR. There's I, and there's R. I is negative because the current's going up through the resistors rather than down through them. The current going through resistor RE1 is just beta plus 1 times IB1. I know that because the currents through this node have to satisfy the Kirchhoff current law. When I look at these two currents, since they're going through the same wire, they have to equal one another. I can conclude here that IB2 is beta plus 1 over beta times IB1. From my voltage equation up here, I can solve for IB1. It's going to be minus my load voltage divided by beta times the resistors. Therefore, IB2 is beta plus 1 over beta, and now I can substitute in for IB1. Let's now find our Thevenin equivalent voltage and Thevenin equivalent resistance. So for the Thevenin equivalent voltage, we just have to assume an open circuit at this point and measure the voltage. So it's going to be a voltage divider set up by resistors R2, R3, and R sub S. We have R2 in parallel with R3, and then those divide over the source resistance R sub S. The Thevenin equivalent resistance is found by just assuming that your source is turned off, which grounds it. We then have R2 in parallel with R3 in parallel with RS. I'm now going to apply the Kirchhoff voltage law around this loop. First, we have a voltage rise of VTH. Then we have a voltage fall of IB2 times R Thevenin. And then we have a voltage fall. The current is beta plus 1 times IB2. And then the resistance is RE. Those have to add to 0. I can solve for my Thevenin voltage. I can factor out IB2 and then just write all the resistors. I know what IB2 is, so I can substitute this down into my expression. I now have both the load voltage and the Thevenin voltage in this equation. I'm interested in knowing the load voltage divided by the Thevenin voltage. So whatever's in the denominator, I'm going to move it to the numerator, and whatever's in the numerator, I'm going to move it down to the denominator. First, we have beta squared. Up here, we also have beta plus 1 squared, and we'll have it with the other term if I divide RTH by beta plus 1. So here's what I'm going to do. I'm going to factor out beta plus 1 squared. I'm going to write this in the numerator. And then I'm going to write this in the denominator, remembering that I need to divide RTH by beta plus 1. So beta squared over beta plus 1 squared, that's nearly equal to 1, so I'm going to ignore it when I rewrite. Now let's write our load voltage in terms of our source voltage by substituting in for our Thevenin equivalent voltage here. So let's go ahead and make that substitution for the Thevenin voltage. Then I'll write the rest of the expression. Now for this R sub E, I'm going to substitute in what I defined it as. And now for my Thevenin resistance, I need to make a substitution as well. And down here where I have beta plus 1, I'm just going to approximate it as beta. If you look at my expression for the load voltage in terms of the source voltage, it's identical to what we found earlier by inspection. The gain of a cascode is pretty much the gain of a common emitter amplifier. The only difference is that here you have 2 transistors instead of 1, and you have better high frequency performance. Let's work an example to see how much better it can be. We're going to be working 2 examples. In the first example, it's going to be a standard common emitter amplifier. And then in the second example, it's going to be pretty much the same, except we've converted it into a cascode. Let's work the standard common emitter configuration amplifier first. Let's do a DC analysis first. So we have 10 volts up here at the power supply, and we have 2 10 kilo ohm resistors. That makes it pretty easy to find the base voltage since it's a nice even divider. The voltage at the emitter is going to be 0.7 volts down, and our emitter current, our DC emitter current that is just 4.3 volts divided by 1 kilo ohm, giving me 4.3 milliamps. We now have enough information to estimate little r sub E. It's just 26 divided by my emitter current expressed in milliamps. Here it works out to about 6 ohms. We'll estimate beta to be in the neighborhood of 100 like we usually do. Let's write an expression for the overall gain by inspection. I'm going to use impedance reflection for the gain portion rather than the input portion. So for the input divider, I'm going to stop at the base. Now for the rest of the gain, we just need the resistors attached to the collector divided by the resistors attached to the emitter. Attached to the emitter are basically 3 resistors plus those reflected from the base. So let's do the emitter side first. We have 1 kilo ohm down here that's in parallel with 5. Those are in series with little r sub E, which is in series with everything reflected over from the base side. On the base side, we have 10 kilo ohms in parallel with 10 kilo ohms in parallel with 100 ohms. And we're going to have to divide that by beta to use impedance reflection. Minus 41 is how that works out when you plug everything in. Let's clean up our drawing a little bit and analyze the high frequency performance. We'll start with CBC, the base collector parasitic capacitance. I'm now going to redraw the input side of the circuit and convert CBC into the Miller capacitance. Let's find the Miller capacitance first. It's just going to be CBC times 1 minus our gain, and our gain is negative 41, so it's going to be 1 plus 41. What's connected to the Miller capacitance is a Thevenin equivalent resistance and a Thevenin equivalent source. And if I were to label that here in the circuit to the left, I need to be looking in this direction from our capacitor. The only thing that really matters if I'm trying to find the corner frequency is the Thevenin resistance, so I'm going to skip finding the Thevenin equivalent voltage. If I look down from these arrows, I have a number of resistors moving away from us or headed away from us. So I've got a 10 kilo ohm resistor going to ground. And then I've got another 10 kilo ohm resistor going to ground. Then I've got a 100 ohm resistor going to ground. And then I have a resistance through the base, and I need to use impedance reflection to find it. So on the emitter side, we have RE plus 5, and I'm going to have to multiply that times beta to bring it over to the base. If we calculate it all out, we wind up with 90 ohms. This is clearly a low-pass filter. It's a one-pole low-pass filter. Let's find its corner frequency. The corner frequency of a low-pass filter is 1 divided by 2 pi times the RC time constant. So here we have RTH, and we have our Miller capacitance. This works out to 5.1 megahertz. If you're going to use this amplifier at low frequencies, frequencies below 432 megahertz, no problem at all. But what if you need it to work at 10 megahertz? Well, in the next example, we're going to try it all with a Cascode, and you'll see that the situation improves. So try to remember this number, 5.1 megahertz, because that's what we're trying to beat. Before I go on to the next example, though, I want to point out what the effect of the other capacitance is. What does the base emitter parasitic capacitance do to the circuit? Let's clean up our drawing just a little bit, and we'll now consider this capacitance. We are again going to have a Miller capacitance, and that Miller capacitance is going to be given by CBE times 1 minus our gain. But what's the gain of a common collector amplifier? You see, it's non-inverting. The signal here is pretty much the same as the signal here. They're 0.7 volts apart, and the little R sub E makes a small difference, but basically it's a non-inverting amplifier with a gain of about 1. So this number here is nearly equal to 1. The Miller capacitance can be approximated here as 0. Basically, the capacitance becomes so small that we don't have to worry about it at all. Now, how about on the output side of the circuit? We've already determined the effect of the base collector capacitance on the input side, but how about the output side? The CBC capacitor here, I can kind of slide it over to here and connect it to ground, delete it from the circuit, and call it C2. C2 is our base collector capacitance, and it gets scaled by 1 plus 1 divided by our gain, which is 41. To the left, we're going to have some Thevenin equivalent resistance, and again, we have something that looks like a low-pass filter. In this case, RTH is just 1 kilo ohm from our load in parallel with 1 kilo ohm from our output impedance, so it's about 500 ohms. When you plug in the values, you wind up with a corner frequency of about 39 megahertz. It shows that the output side is less of a problem than the input side. Let's now work the same example, replacing the common emitter amplifier with the Cascode. I've not changed any of the resistors on this circuit, so the overall gain is going to be the same as it was in the last problem. It's minus 41 here. We know that the base collector parasitic capacitance is going to be a problem. To know how much of a problem it is, though, I need to know what the gain is of just the first stage of this amplifier. What's the gain of the common emitter portion here? I don't need the overall gain. I need the gain between this point of the circuit and this point of the circuit. Well, if we label this impedance here as our input impedance, then we can write an expression for the full gain. This is our input divider. Now the gain of the common emitter stage is minus RE. That's the resistance attached to the collector. And then for the resistors attached to the emitter, we have 1 kilo ohm in parallel with 5 plus another RE down here. In this case, I'm going to use impedance reflection so that the gain is properly apportioned between the stages. So this is our common emitter gain. Now, the gain for our common base stage is going to be the resistors attached to the collector, that is 1 kilo ohm in parallel with 1 kilo ohm, divided by the resistors attached to the emitter, which in this case is just R sub E. This cancels in order to give our net gain of minus 41, but we need to apportion it. It turns out that this is about 0.9, this is minus 0.55, and this is 83. The 25 picofarad capacitor that connects the base of the transistor down to the emitter transistor is not going to matter, just like it didn't matter in the last problem. Let's see what the effect is of CBC for the lower transistor. At the input side, we have a source, a 100 ohm source impedance, then we have two 10 kilo ohm resistors in parallel, We then have our resistance looking into the base of the transistor right here. By impedance reflection, that's going to be beta times Re plus 1 kilo ohm in parallel with 5 ohms. And then we have our Miller capacitance. So we're looking back from the Miller capacitance, and I need a Thevenin equivalent source. The Thevenin equivalent resistance works out to be 90 ohms here. And the Miller capacitance works out to be 8 picofarads. That's 8 times 10 to the negative 12. And we have to multiply that times 1 minus our gain. So that's going to be 1 plus 0.55. This is the one we're interested in, since this is a common emitter amplifier. If you use these two values to come up with a corner frequency, you're going to find 142 megahertz. Clearly, this parasitic capacitance is no longer a problem. So which one is going to limit the performance of this cascode configuration? Let's work through some of the others. Let's clean up our circuit drawing just a little bit. And let's imagine what the signal sees when it reaches this point in the circuit. Well, it's going to see an output impedance of RO looking down into that transistor, and that's going to be a really high number. It's going to see a base emitter capacitance of 25 picofarads attached directly to ground, and it's going to see an emitter resistance R sub E. So at this point in the circuit, we're effectively seeing a 25 picofarad capacitor, no Miller effect needed because it's connected directly to ground, in parallel with R sub E. Well, if you use 25 picofarads and Re in order to find out what the corner frequency is, you're going to find here that it's about 1 gigahertz. So this parasitic capacitance is not really a problem in this circuit. I didn't include the 8 picofarad capacitor in this calculation simply because it's smaller. Technically speaking, I should have added it to the 25 picofarad capacitance, but because the corner frequency here is 1 gigahertz without it, it's not going to matter, so let's just forget it. We now have one more capacitor to consider. This 8 picofarad capacitor is effectively connected to ground because the base is grounded. So here at the output side, if I'm looking from the transistor, we have an 8 picofarad capacitor connected to ground, and we have 1 kilo ohm in parallel with 1 kilo ohm. In other words, 500 ohms coming from this resistor, and that's connected to the collector of a transistor. So from the perspective of the capacitor, we see a low-pass filter. If we use 500 ohms and 8 picofarads to calculate the corner frequency of this low-pass filter, then we wind up getting a number around 39 megahertz. When you get to frequencies that high, you start to have other parasitics in the transistors that start to make a difference that we've not really analyzed here. I ran this in a simulation with the 2N2222 transistors, and LT Spice told me that the cutoff frequency was about 22.5 megahertz. So we're within a factor of 2, which I think is not too bad. Nonetheless, if we compare this performance, our expected performance here of 39 megahertz, to what we discovered when we only had a common emitter capacitor, that is 5 megahertz, you can see that the cascode configuration does give quite a bit higher performance when you're talking about the high frequencies. We've now looked at several different transistor amplifier configurations. In the next video, I'm going to take a step back and look at just the bipolar transistor, and we're going to focus in particular at the transition between the cutoff mode and when current starts to flowing, the forward active mode.